in a HEV, in a hybrid, this affects the fuel economy. Now, whether the customer can tell that or how well the customer can be made aware of that is debatable depending on the architecture. But when you get to a plug-in hybrid or a full EV, this is a really big effect to the customer. They're going to see things, they won't be able to drive as far, or their engine will come on, their fuel economy will drop significantly, and it will cost them more money to run. So this is why we're really interested in the aging process, and it's really so we can optimize the size of the battery we're putting in to start off with. So how do we do this? Well, you've got to understand what's going on at a base level. You've got to understand where these things that can go wrong with the lifetime are coming from. Unfortunately, that involves getting our hands dirty in the chemistry. So this is an example of how the battery, when everything's going right, this is the sort of thing we would expect to see within the battery. It gets more complicated when we try and work out all the ways it can go wrong. And so it's really, we have to start understanding, tracking these ways that it can go wrong, these ways that we can lose energy and lose power from the battery, in order to be able to work out how we can engineer around that at the systems level. So you take those underlying chemistry reactions, and you try and build that up. How does that propagate throughout the system? So you have your aging mechanism, so this is coming from the cell chemistry up to the aging mechanism. And then you can start to track to the real world behaviour. So now we're seeing things that customers can do, that we can do to the vehicle that will age these cells. So then the next step is really, what can we do to try and stop these? Now we understand what the causes are, now we understand what they mean at a system level. It gives us a chance to have a look at the way we can get around these and really optimise the engineering and take weight out. Where can we take weight out? What is the acceptable areas where we can, where it actually doesn't have an effect on aging? And so this process allows us to go all the way up to the systems level and optimise the packaging around these cells. So just a little word about the actual chemistry that's going on in the cells. So this is a nice complicated slide that goes through kind of what's going to happen with the technology over the next few years. So as well as optimising what we see in the battery, the engineering, there's also the materials research that backs it up. And so if we take a broader overview of that, we've got, and for the next sort of 10, 15 years, it's going to be lithium-ion chemistry. It's still going to have the best energy density, best power density. But over time, we're going to see new technologies come along. And this is, some of you may have heard of the air batteries coming along. They've been promised for about 25 years, that they're 25 years away, and they're still 25, 30 years away. I think it'll be a while before there's still fundamental science understanding that needs to go into the sort of air batteries, and once you get through that, there is a huge engineering challenge surrounding those as well. And so they're probably quite a while off still. And in all honesty, if anybody ever shows you a roadmap that goes for more than 10 years in battery chemistry, it's quite close to guessing at that point. There's technology roadmaps for the next 10 years after that. It really is still waiting on the scientific discoveries to make the breakthrough, and in order that we can continue with this energy density increase. So specifically the research that we're doing at Warwick Uni, it's taking this whole system approach, and it's trying to understand what can go wrong at a materials level, and also how we can get costs, how we can improve the energy density within the battery system itself, the packaging around the battery. And so this is just an example of so these are the research streams that are going on at the moment within Warwick. So it's looking specifically at that aging problem, it's trying to model the behaviour of the cells, trying to look forward, see what's coming up, see how we can build that into the strategy, trying to work out how we control those cells, and also working out how we optimise the design and packaging of the battery. So just in summary, materials research will be the way that it makes battery technology more credible. There's no doubt about that. If you want to improve the energy density, it's got to be at the materials level. But we're not quite there yet. right, we can still get around a lot of the problems out there by understanding it and implementing elegant battery pack design and really working out our systems engineering, understanding how people are going to interact with these. And when we get through that, we'll be able to have far more credible electric vehicles than are out on the market now. And that's just really, that's standard basic engineering, understanding how people are going to interact with the component and really finding design routes around these problems. So that's kind of, in summary, we're almost there with the engineering side, but it's the materials research is really going to push it into a sort of competitive with the range and power that you see on internal combustion engines.